Hey everyone! Welcome back to Bug no Jutsu. In today's video, we're solving an interesting problem that's all about counting the number of unique ways to represent a number as the sum of powers. We'll break it down step by step, walk through an example, discuss my approach, and finish with complexity analysis and key insights. We are given two positive integers, n and x, and our task is to determine in how many different ways we can write n as the sum of unique positive integers, where each integer is raised to the power of x. The important point here is that the integers we choose must be distinct, so we cannot repeat the same number more than once in a single combination. Also, the order of the numbers does not matter. Choosing the numbers 2, 3, and 5 is considered the same as choosing 5, 3, and 2. The result can be extremely large, so we return it after taking the modulo with 10 to the power of 9 plus 7 to keep it within manageable limits. For example, if n is 160 and x is 3, one possible way to represent n is by taking 2 raised to the power of 3, 3 raised to the power of 3, and 5 raised to the power of 3. When we calculate each of these, we get 8, 27, and 125, and their sum is exactly 160. This is one valid combination, and there can be many others depending on the values of n and x. Our goal is to count all such distinct combinations. Let's take a small example to see how it works. Say n equals 10 and x equals 2. This means we need to find all sets of distinct natural numbers whose squares add up to 10. We start from the smallest square, which is 1 power 2 is equal to 1. If we try 1 plus 9, we get 1 power 2 plus 3 power 2 is equal to 10, that works. What about other combinations? If we try 4 power 2 is equal to 16, it's already larger than 10, so it's not valid. Similarly, 2 power 2 is equal to 4 and 3 power 2 is equal to 9 can't combine in any other unique way to make exactly 10. So in this case, there's only one valid combination, 1, 3. This example is small, but for bigger n and x, the number of combinations can grow or shrink depending on the powers. My approach uses recursion with memoization to explore all possibilities efficiently. I think of it like this. We start with a current number j, and at each step, we have two choices. Include j power x in our sum and move to j plus 1. Skip j power x and still move to j plus 1. This way, we're exploring all combinations, but because we always move forward to the next number, we avoid repeating the same combination in a different order. We keep track of the remaining sum we need to reach n. If at any point the remaining sum becomes exactly 0, that means we've found a valid combination, so we count it as 1. If it becomes negative or j power x is greater than the remaining sum, we stop exploring that path. Now, without optimization, this would repeat a lot of calculations for the same, remaining sum, starting number, pair. So I use memoization, caching the results of each state, so if I hit that exact situation again, I just reuse the answer instead of recomputing it. This makes the solution much faster and lets us handle larger inputs easily. In terms of complexity, the time complexity is roughly n times root n, because for each possible starting number, we explore two choices, but memoization ensures each state is computed once. The number of possible starting numbers is about root n when x equals 2, and it's even fewer for larger x. The space complexity is also n times root n, due to the recursion stack and the storage needed for our memoization table. A few key insights from this problem. The moment you realize it's about combinations and not permutations, the solution space becomes much smaller and easier to handle. Powers grow quickly, so as x increases, the search depth reduces dramatically. Memoization is the game changer here. Without it, the recursion would explode in complexity and would not run for larger values of n. Thinking of the problem as a decision tree, include or skip, is a powerful approach that works for many subset and combination problems. And that wraps up today's problem. We broke down the statement, walked through an example, and saw how recursion with memoization can efficiently solve it without overcounting. If you found this explanation helpful, make sure to drop a like, subscribe to Bug no Jutsu, and share this video with your fellow coders. And if you have a different approach or a cool optimization, let me know in the comments, I'd love to check it out. Until next time, keep coding and keep improving.